Hello, everyone who might be watching my presentation. Welcome to high-speed flight. I'll be going over a lot of the things relating to high-speed flight. However, I also want to be going over a little bit of LD max and high-altitude flight and the aspects that kind of feed into those. So, starting off, VNE is the never exceed speed on any given plane. If you see right here, it's this red dash. That is the never exceed speed. In relation over here on the other side, these are the stall speeds, where the little bars end. Now, on regular general aviation aircraft, usually those two are never going to be anywhere near each other, like you can see here. However, for jet planes, planes that fly high, planes that fly fast, those numbers are actually going to be very close to each other. The MMO, the maximum Mach number, and the stall speed are going to be very close to each other. And I'll explain why this is significant in a moment. So the coffin corner, actually called the Q corner, Q is the variable standing for dynamic pressure, is what happens right here. When you get high enough where your slow speed stall and your overspeed Mach buffet will meet. This is significant because with altitude, air becomes less dense, right? So your true airspeed will increase with your altitude. However, that also means that your stall speed will increase as well. The kicker here is that your true airspeed to reach your MMO will decrease with altitude. So going back to this little infographic, you can see as your altitude goes up, the slow speed stall, the airspeed at which you'll reach that stall, it increases. However, the Mach buffet speed will decrease. So they meet right here, and this is the area that you want to be aware of. That's the area you want to stay away from flying at lower approved altitudes. The approved altitudes I'll get to a bit later. So dangers of transonic flight. Transonic meaning at any point when an air particle will begin to go over your wing faster than the speed of sound. If you have conventional control surfaces on your plane, they may start to buzz, which could cause structural damage, especially if it's something that the plane isn't really rated for. So watch out for that. Your wings could fall off. It's not a good thing. In addition, you'll have airflow separation, which is what happens right here. Supersonic flow happening right here. However, it'll turn subsonic and you'll have this separation right here, which will go off and cause problems such as loss of lift. That's something that happens to Mach tuck. This is referring to this little separation right here. It pretty much is a loss of lift behind your control surfaces, which when it's affecting your horizontal stabilizer, that means that your stabilizer really isn't getting any lift at all, right? Because it's behind your wings, which is, where the supersonic flow is happening. So if you lose, the lift that's happening over your horizontal stabilizer, what happens? You lose that, your nose starts to pitch down, which is something at that airspeed that you may or may not be able to recover from, It's a scary thing. However, it's something that can also happen if that loss of lift only happens on one wing. That wing that has the loss of lift versus the other one will pitch down. You'll enter into a spin, which again, you may or may not be able to recover from. It's a scary thing. So to combat these dangers, which is something we definitely want to do if we want to fly at high speeds like that, we have a number of modifications to our aircraft designs. We have, first off, the supercritical airfoil right here, which is a wing design slightly altered from the one that we're used to seeing in below sonic speeds. It's a bit modified so that the shock wave is much weaker than it would be on the other one. We also have sweep back wings. Their purpose is to delay the onset of compression effects, kind of like the supercritical airfoil. And they also reduce the magnitude in aerodynamic force changes, so they just make it a bit more soft as you flow through those stages. In addition, we also have buffet tabs right here on the lower edge of the wing, which just serve to decrease that buffet as you're, traveling through the transonic speeds. It'll hopefully decrease that buffet and give you more controllability over all of your control surfaces. So, sweep back wings. There are, unfortunately, a lot of disadvantages to this aircraft design. Most supersonic aircraft will still choose to go with this design. However, it's important to be aware of the downsides. First off, the tendency for the wingtip to stall first is bad because that's where your aileron is. That's where you're controlling your craft. So if that stalls first versus the inner part of the wing right here, you're losing that extra controllability that you would normally have if you're going into a stall. In addition, it'll reduce the effectiveness of the high lift devices, such as the flaps along the inner parts of your wings. And you'll also have an increased Dutch roll tendency. This is what happens, such as in this infographic, when you're flying along, somehow you get unstabilized so that one ring is facing into the wing more than the other. This is catching more air right here, right? So this wing is going to be pushed back farther than this wing. The plane will shift, and then the exact same thing happens on the other side. So this wing is now getting more of the air force. It'll be pushed back more. And that's how the Dutch roll happens. It's just over and over, this forward and back until you can recover from it. Okay, so what happens as a plane goes supersonic? This is referring to what will happen as soon as any air particle over your wing goes supersonic. And indeed, they will probably go supersonic over your wings faster than anywhere else on the plane, just because that's what the wings are meant to do. The air over the wing goes faster than under the wing. That's what creates lift. However, this will also produce shock waves. There are 3 types of shock waves. The first is oblique, which is what will happen when a supersonic airstream is turned into the preceding airflow. You have the normal shock wave, which is what happens when the shock wave is perpendicular to the upstream flow. This will also cause the flow behind the wave to be subsonic. And the expansion wave, which is what happens when the supersonic stream is turned away from the preceding flow. So we have the 3. It's when the supersonic airstream is turned either into it, perpendicular to, or away from the preceding flow. Here's a little chart that shows 2 of the types of shock waves that can happen as you break the sound barrier. You have the oblique shock right here that happens at both the beginning and the end, and the expansion fan that happens right at the crest of the wing right here. As for the normal type of shock wave, picture like a square box, not really aerodynamic at all, right? Kind of getting thrown into the wind so that it breaks the sound barrier. That's kind of the normal shock wave that would happen there. Okay, the lift drag max is, I'm gonna fast forward right here to this infographic. So I'll come back to that information in a second. I'm going to start by explaining drag a little bit here. You have 2 types of drag, parasite and induced drag. As your airspeed increases, parasite drag increases, which is drag that does not affect your lift. However, as airspeed increases, induced drag, which does affect your lift, decreases, right? So no matter how fast you're going, you're either going to be affected by one other or both. Well, always both, but one or the other to varying degrees. And the spot where you want to be, the sweet spot right here, is where you're going to have the least amount of lift. The least amount of drag. This will give you better speeds, better economy, better lift, the whole deal. So that's right where you want to be. Going back to this, if you are slower than the LD max, that's going to be your slow flight region. This is also known as the region of reversed command, and that's where you're going to get your dynamic instability, which is, if you're flying along and something, maybe some turbulence pushes you off course, you're going to increasingly get more and more off course. That's what dynamic instability is. As opposed to dynamic stability, which is what you'll get when you're on the other side of the LD max, which is the normal flight. When you're in faster than the LD max, if you get pushed off course somehow, your aircraft will eventually return back to the point where you were before you got pushed off course. And I experienced this when I was learning to fly. My flight instructor had me trim out my airplane. I was on the faster side of the LD max. She had me trim out my airplane, and then she had me let go of my controls. And the first thing that happened was the airplane started to pitch down, kind of at an alarming rate, and I was about to freak out, but then the airplane started pitching back up, and it pitched up, 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 and then back down, and then back up, and each time the waves started to get smaller and smaller until it kind of was back to right where it was before I had let go. And that was really interesting to me. It's kind of an example of dynamic stability in flight, and that's what you want to have, so that if anything will happen, it's easier to get back on track. Okay, so finally, I'm going to be going over high altitude aerodynamics. This is referring to anything over flight level 250 or 25,000 feet. This is the level at which everyone on board must be provided with oxygen, because if the cabin depressurizes, you're going to have seconds before your brain processes slow down to be enough where you're just completely hypoxic and out of it. So yeah, definitely have oxygen for everyone on board. But the kicker with high altitude aerodynamics here is that your true airspeed increases with altitude. However, your indicated airspeed stays essentially the same. So true airspeed increases, you're going faster, that's great, you'll get to your destination. However, the effectiveness of your controls are dependent upon the indicated airspeed, which does not change much due to altitude. So you're going to have a reduction in the controllable range of your airspeed, which is something that you definitely need to know about if you're operating at high altitudes. So maximum operating altitudes. I put the same infographic as before to kind of go back to these maximum operating altitude factors. They're determined by 3 characteristics unique to each type of plane. It's going to be a combination of the lowest of the maximum certified altitude, which is usually structural and refers to the pressurization load limits on the fuselage. Also the thrust limit altitude, which is the prevailing operating weight and environmental conditions. Usual controlling limit when available thrust may be very small. So that's kind of this line right here. That's what it's referring to. And finally, the Buffet limited maximum altitude. That's the altitude at which load from maneuvering or turbulence experienced will be low enough or high enough so that you won't experience a low speed stall buffet or a mock stall. So it's going to be a combination of those 3. And that's usually going to be an altitude lower than your coffin corner. So they'll want to keep you safe. They're not going to give you a high altitude where you're just going to fall out of the sky. They usually don't want that. So in conclusion, while knowledge is very important, it could also save your life. Understanding is the key to true knowledge. And if we understand the factors that go into high altitude flight, if we understand the factors that go into high speed flight, you're going to understand it, you're going to know about it, you're going to know what to do if anything unexpected comes your way while you're operating in these conditions. I want to end by saying a little something about military pilots. When they're learning how to fly, it's required that they know everything about the conditions that they are flying in, about the aircraft. It is much more intense and in-depth than for general aviation craft. For a little example, I had the opportunity to listen to a speaker who was a U-2 pilot. That's this type of plane. It's generally referred to as like spy planes, something like that. It's a plane that is able to fly up high in the stratosphere. And to give you an example of how tricky this plane is to fly, going back to the very beginning there, it's stall speed and its MMO speed. The sweet spot is within 5 knots, right? 5 knots slower, you will stall. 5 knots faster, you'll exceed that MMO. So this U-2 pilot, they have to be so exact. They have to rely on the autopilot. It's something very difficult, and they're just required to know everything about flight in the stratosphere, about high-speed flight, and it's very impressive what they can do. So to conclude, just stay knowledgeable, learn what you can about where you're flying, and thank you for listening.